Hello, it's Keith here, and today we're going to do a special episode where we're going to look at the beginnings of programming the Game Boy and the Game Boy Color. Now, we looked at the Game Gear last week, and there's some commonalities, but the Game Boy and the Game Boy Color are much more difficult for us to program if we're a Z80 programmer coming from a computer than the Game Gear and the Master System. And the main reason for that is that the Game Boy and the Game Boy Color are not a true Z80 processor. Now, if you're not familiar with the background of the Z80 processor, the Z80 processor was based on Intel's 8080 processor. It was heavily upgraded by Zilog and became the Z80 that we know today. However, the Game Boy Color processor is also based on the 8080, but it does not have all of the functionality of the Z80, and it actually has some strange functionality that is exclusive to the Game Boy's processor, and for that reason it's sometimes referred to as the GBZ80. But to be honest, even though it's not a true Z80, it's close enough that we can work with it. And so if you're familiar with Z80 programming, with a little bit of compromising, you can program it just fine. And it's a really interesting, nice system to program, technically speaking. So I think it's worth looking at if you are interested in multi-platform programming. So let's have a look at the start, and let's have a look at the hardware itself. So the first thing to know is that the Game Boy Color is backwards compatible with the Game Boy. So a Game Boy game will work on the Game Boy Color. And if you're careful, you can make a game that uses the Game Boy Color's color screen, but still works just the same way as on the Game Boy. So let's have a look at the hardware. Well, the CPU, as I said, it's not a true Z80, but it's close. It's 4 MHz like the regular Z80, but on the Game Boy Color, there is a special function you can call which actually doubles the speed of the internal processor. Now, obviously, this will make it tricky if you want to make a game that uses that 8 MHz mode on the Game Boy Color, but is only 4 MHz on the Game Boy, but you could do it if you wanted to. Now, the basic Game Boy has 8 kilobytes of RAM, but the Game Boy Color actually has 32 kilobytes, so more memory on the Game Boy Color. On the Game Boy, though, if you need more memory, you can use special cartridges which have swappable banks built into the cartridge. So even if 8 kilobytes isn't enough for you on the regular Game Boy, there are other options there. Now, the system has its own dedicated video memory. There's 8 kilobytes on the regular Game Boy, 16 kilobytes on the Game Boy Color, and that's why later on we'll see the Game Boy Color has twice as many tiles it can do. That's because of that extra memory. So the screen on both systems is 160 by 144, which is the same as the Game Gear. So again, if you're looking to program a game on both systems, that makes it nice and easy for you because you're working to the same screen size. Now, the number of tiles, we did cover tiles last week in the Game Gear systems, but if you didn't see that, we'll cover them a bit in a moment. The tile map is a grid of 8 by 8 pixel patterns that repeat along the screen, and the important thing to notice is we would need 360 unique patterns to fill the tile map where every tile was different. Unfortunately, on the Game Boy there's only 256, and that means that it's really impossible for us to have every single pixel on the Game Boy screen different. We can do that on the Game Boy Color, and if you look at Game Boy games, you'll notice that on the regular Game Boy, the title screens of the games are often have sort of blank patches and don't have all unique tiles because of that limitation. But on the Game Boy Color, you'll often see a full screen bitmap because it does have enough tiles to do that. Now, as well as tiles, we have the more advanced sprites. These are all 8 pixels by 8 pixels square. There's a limit of 40 on screen, but there is another limitation of 10 per line, and this is a hardware limitation. If we tried to put all 40 onto the same line, some of them would flicker, so obviously we'd have problems there. Now, the Game Boy and the Game Boy Color are both 4-color systems, technically speaking, so each tile is 4 colors, and each sprite is 3 colors with 1 transparent color. So it's essentially a 4-color system. But on the Game Boy Color, there are 8 palettes we can define, 0 to 7, and these will have 4 different colors for each one, so that we can keep the black and white compatibility, but we can have different colors on our more advanced system. And both of these screenshots you can see here of my little test program, which we're going to look at next week, this Hello World test. They're the same program, but the top color version has had color palettes attributed to it, and I've simulated a kind of CPC color palette here. But we could have all of these squares in this. This is actually done with patterns. There's no sprites here. So we could actually have Chibigo's face different color to the shoes if we wanted using those palettes. So the Game Boy also has its own special sound chip. It's quite a nice little sound chip. It's capable of 3 sound channels, 2 of which are square wave channels, which make sort of beeps, and one is It's called a wave channel, which may make it sound like it can do speech, but it's very basic. It can't really do anything that great, but we can use it to simulate a third sound channel if we want, and it also has a noise channel, so it's pretty reasonable. A little bit more tricky because it's only got the 2 basic channels to use than maybe the Game Gear sound chip, but it's perfectly capable, so it's not so bad. Now the GBZ80, what's the differences? Well, I'm afraid there's quite a lot of differences. Well, the first thing is we have no shadow registers. These were added to the Z80, they weren't in the original 8080, and the Game Boy doesn't have them either. As well as that, we've got no IX and IY, they're gone. We've also got no refresh, and we've got no interrupt pointer. Part of the reason for that is interrupt mode and 1 and 2 don't exist either. We'll actually have a look at all of the commands in detail in a moment, just to show you what's there and what isn't. But there were some other basic limitations we need to discuss. So LDIR and LDI don't exist. That's a bit of a problem, but all of the commands that we're going to discuss here, even though they don't exist on the Game Boy, we can simulate them, and I've written macros to emulate a lot of them. Just last week I actually did a bit of an experiment, and I managed to put Arcus Tracker, the Amstrad CPC sound tracker software, to the Game Boy. I wrote a very basic AY emulator to emulate the sound, and I wrote macros to simulate the quite wide range of commands that Arcus Tracker needed that the Game Boy Z80 didn't have. So it's annoying, but it's perfectly possible. So also, as well as that first limitation, we have the limitation, if we want to load a register pair, we can't do it. We have to do it one at a time. So if we wanted to load BC from a memory address, we'd have to load A from the memory address, load it into C, and then load A from the memory address +1 and load it into B. Or we'd have to set HL to the memory address, load C from the memory address, increase HL, and then load B from the memory address. So we can work around it, but it's a lot more tricky, unfortunately. Now, another quite curious thing is the in and out command don't exist. So you might think, well, how do we get to our hardware? But it's actually memory mapped, and we're going to have a look at that in a moment. Now, that's the first set of limitations, but there's a few other quirks that we do need to know about. We can do INC, BCD, and HL, and DEC, BCD, and HL. But if we've got HL, if we've got one of those pointing to the sprite memory, then it can corrupt the sprite memory. So just something to bear in mind. Maybe you want to not use those commands, or if you're being very careful, you can. But if you're not using sprites, don't need to worry about it though. The halt command is quite curious too. As part of the power saving options of the Game Boy, if you disable interrupts and halt the CPU, it will actually not, on a regular computer, that would basically crash the machine because the interrupt would never fire, so the halt would never carry on. But on the Game Boy it will carry on, but because of a quirk it actually skips the next command after that halt. So if you want to use that functionality, you have to put a no-op after the halt so that that sort of bug will skip the no-op and everything will carry on normally. But from my point of view, I would never disable interrupts and put a halt, because that's just bad programming, because in every other system that would lock the machine up. So it doesn't cause as much problems as you might think. So those are the basic commands that are missing. There's a lot of others, but we'll have a look in more detail. We do have some benefits. We have a swap command. What does this do? Well, it's the equivalent of rotating all the bits in a register 4 times. So it swaps the bottom and top nibble, and it does it in a single command. Very nice command. Quite a shame the Z80 doesn't have it, but there we go. We then have this rather strange command which loads from a memory address with starting in FF plus C, and then that loads from and to A. This is kind of like the out command. The memory addresses from FF00 to FFFF have special purposes on the Game Boy, and so being able to use the C register as a sort of offset to that, it allows us to do things a little bit more quickly within that memory range, and we'll have a look at that in a moment. Now, I said LDIR and LDI were missing, but there's a special command that the Game Boy has that kind of makes up for these. We can use LDI with HL, and this will read in from HL into a register and then increase HL. So it's all one part of one command. So this is kind of our equivalent there. So let's have a look at the cheat sheet. If you've seen my regular cheat sheet, I've got another version of it, which you can see here. And what I've done is I've got all of the commands on that original cheat sheet, but you'll notice some are greyed out, and the greyed out ones are missing. These are ones that the Game Boy, the GBZ80 cannot do. You'll also notice some are in bold. This means that they're actually new commands, or that the command has changed in some way. Now this LDA from address, that command exists perfectly normally on the Z80, but on the GBZ80 it actually compiles to different bytecode, so you have to be careful there. And you'll see these commands are new, and you'll see because they're in bold, and you'll also see some of these commands have bugs or quirks to them, and I've marked them as well. And at the very bottom of this list you'll see I've got some notes here, and depending on the assembler you use, some of these commands may vary in their definition. So some systems call LDI LD from HLI. It just depends what system you're using. Now I should say at this point, you can't use a regular Z80 compiler to compile. So if you're using WinApe for your other systems, that's not going to work. In the case of the GBZ80, you need a special compiler. What I'm using is Vasm. Vasm is a great compiler that can compile to almost every processor you can imagine. So if you've been following my GBZ80 project, and if you're interested in this, you should be, because that covers the Game Boy Color and the Game Boy, and also the Master System and Game Gear. But that was compiled almost entirely with Vasm, and you can compile every version, and it works absolutely great. So I'd highly suggest Vasm if you're looking to do assembly Game Boy programming. If you're looking to do C, there are other alternatives, but it was assembly I was interested in. So yep, we've got all kinds of commands here. Most of them aren't particularly exciting. As I say, we've got these swaps, and you'll notice they're in bold because that means they're exclusive to the Game Boy Z80. You've got a stop command here as well, which pauses until a key's pressed, and again, that's a battery saving option. But generally speaking, the vast majority of these commands aren't too exciting. Really all we need to know is the commands that are missing, so we don't use them. And if we do need to use them on our other systems, we have to fake them in some way. For example, if you need the IY registers, what you can do is you can use a defined memory address and simulate that I register by loading in to that memory address. So let's just have a quick look at how I've been doing that. So if you look here, this is a set of definitions that I've created for the Game Boy processor, the GBZ80, and these will emulate all of the functionality that I needed to get Arcus Tracker working, and also for my Grime project. So this is the current best version I've got. Some commands still aren't emulated, but I think I've done most of them. So EXSPHL, that doesn't exist, but if we do a few tricks and a few push pops, we can fake it. When it comes to commands like the IX and IY registers, we've defined some memory addresses here at the top of the Game Boy's memory, and we're just basically using those to fake it. So it can be quite a pain, and you can see there's a lot of commands here. In some cases I'm swapping, like if you look at EXX, this is a very small command. This is a 1 byte command on the Z80, but it's very, very large on the GBZ80. So if you were writing stuff from scratch, I wouldn't really recommend using a command like that. But if you quickly need to port something like I did with Arcus Tracker, this is good enough. And the thing is, the Game Boy, because it's got hardware graphics, clearing the screen on a Game Boy using the tar map is many, many times faster than clearing the screen on the Amstrad or the Sam Coupe. So what you're potentially losing in these larger commands, you're saving in your graphics work on the Game Boy. So I don't think it's going to cause you a major problem. Now, the way you use these in the code is you just sort of use these commands in the code, and the assembler automatically converts them to the equivalent commands. But because this isn't something that the Z80 will recognize, there is a Z80 equivalent. So if I just find that, but you can just see on the Z80 it actually just compiles to the command itself. So if I want to compile for both the Z80 and the GBZ80, I use this command in my code, knowing that it will convert to whatever is the best thing for that system. So that's how I've been working around the limitations with regards to doing the Arcus Tracker thing. But as I've said already, if you're programming for the Game Boy from the start, and you know you want to compile for the Game Boy and the Amstrad, or the Game Boy and the Game Gear, just try not to use these commands that the Game Boy doesn't have. Aim for your minimum target, and then you can use all those extra registers and all those extra commands in the Amstrad exclusive code. The graphics code, for example, for the Amstrad, the Game Boy would never use, so use them there. But the common logic code of your game, try to stick to the Game Boy's limitations of not having those extra registers, not having those extra commands, and you should be okay. That's what I did with GBZ80, and it worked quite nicely. So anyway, enough of the CPU. We're going to cover all of this in greater detail later. This is just an introduction, but I felt it was important to mention in some detail the problems you were going to face with the processor. And this file here is available for download on my website, and the emulation, the GBZ80 emulation definitions here, which are for VASM or for they should also work for WinApe. Well, only these ones will work for WinApe because, as I said, you can't compile Game Boy code with WinApe, but you can use those as well. So, well, we mentioned very briefly tiles and sprites and things, and if you are interested in this, please go back and look at my last episode, which was about the Game Gear and the Master System, because I discussed tiles and sprites in those as well, and I'm going to discuss them a little bit more briefly here because I'm hoping a few of you actually understand the concepts of these already. Well, a console system, and an 8-bit console system, generally speaking, will have two different kinds of graphic. Tiles, they are in a grid format. They have to be in a limited grid format. And what you do is you define your tile patterns, and then you define which positions in the grid use those patterns numerically. So, for example, this star could be number 3, the background could be black, the black background could be 0, and the grass could be number 2. And then you define in the positions in the tile map those numbers, and the hardware will draw the graphics according to that tile map. And that's why it's so fast to clear the screen, because we're only writing a few bytes here. In this example here of an 8x8 tile map, we're only writing 64 bytes to fill the entire screen. Whereas on the Amstrad, we'd be writing 16 bytes just for this one star pattern, and then another 16 for another 16 here, because of the because it's using 2 bytes per line and 8 lines for an 8x8 pattern. So as I say, the hardware tile map is very fast. Now, that has a limitation that everything has to be in a grid format. So what if we want to have a character that can move around? Well, we do that with our sprite layer, which is typically above the background layer, and we can define that. Now, the sprites on the Game Gear and the Game Boy, they're 8x8 pixels, which is very small. But a big sprite we can just break up into 8x8 chunks and move all of the sprites together to allow us to make a big sprite out of lots of small sprites. So again, a little bit of a pain, but not a major problem. Now, the Game Boy Color has some extra benefits. It has color, obviously, more memory, faster processor, and instead of just the black and white, we can now define these 8 color palettes, 0 to 7. So we actually have quite a lot of color options. We're using 5 bits per channel, so the Game Boy Color surprisingly beats the CPC Plus, but it doesn't matter. We're going to look at how to do color on all of our systems later, and I'm using a common piece of code that allows you to define in CPC Plus format and works on absolutely every system, which is one of the reasons Gameboy80 got programmed so quickly, because I could do the work basically just once or maybe once or twice, but I could use the same color definitions on all my systems. So we have an extra bank of memory that we page in, and we then define the color for the tiles that we defined for the black and white systems, and this is how it allows us to use the same code for black and white and color systems, because the extra information is held in that extra bank. So if we detect we're on a black and white Game Boy, we just don't do that one extra stage of setting the colors, and that's what we do. Now, if you're familiar with working with computers, you're used to having some built-in firmware ROM that will do work for us. Things are a bit different when you get to working with consoles because they have no firmware, or at least the ones we're working with have no firmware. So when you create your binary file, which is what you need to as a cartridge, it has to be in a certain format, and the first byte in that binary file is actually the first byte of the ROM as soon as your emulator starts, or if you were running it on a real system. So we have to make sure our ROM is in the correct format for that system. So the basic layout of a Game Boy cartridge you can see here. It's not particularly controversial, it's fairly straightforward really. So the first few bytes are the RSTs. Now these are exactly the same as on the regular Z80, and we do have the RST commands, quite surprisingly they do work, so we can use our RSTs if we need single byte commands. But an interesting thing is the interrupts don't work the same. RST7 is interrupt mode 1's interrupt handler. Well, on the Game Boy there's no interrupt mode 1 and there's no interrupt mode 2 either, or there's no interrupt mode 0 either for that matter. So we do have interrupts though, but they work quite differently and they jump to different addresses. So these addresses are used by the Game Boy's interrupts here. Now beyond that there's a bit of unused memory. Then we have a jump block, which is where we define the start of our code, but we only have 4 bytes here, so we can't really do anything except a jump command, and really the space for our code is down here at hexadecimal 150. Now the bit in between that is important stuff for, especially if we're running on a real Game Boy. These are definitions for the Game Boy hardware, and if they're wrong, the Game Boy cartridge won't work, or the Game Boy may refuse to run it. So the first thing we have is a copy of the logo, of the Nintendo logo, and I say a copy because it's built into the ROM as well. I think this is basically a legal trick to they've put the copyrighted Nintendo logo into the cartridge, so if anyone makes a fake cartridge, they can sue them for copyright, breach of copyright, and if they don't put the Nintendo logo in, the Game Boy won't run the cartridge. Now this isn't a problem for our emulators, but if we're running on a real system, we would have to have that Nintendo logo in, or the Nintendo would refuse to boot the cartridge. So like I say, that's something to note. Now, I've only been testing on emulators, but if you want to run on a real system, you need to make sure this kind of thing is right. And what I'd suggest you do is you look for a program called RGB Fix. This is a Game Boy cartridge fixer program which automatically corrects things like that ROM and the checksum and makes sure it will work on a real cartridge. It's not something I'm using here because, as I say, the emulators don't check it. So for simplicity, I've not been worrying about it, but it is something you would need to look at. So then we have a few things that possibly aren't so important. The game name here, well, that can be really anything. It doesn't really matter. It's not something that the system really checks. Now then we need a color, a flag to define whether our game works on the Game Boy, in which case it should be 80, or C0 if it's only for the color Game Boy. A manufacturer code, again not important. We have a flag here for the Super Game Boy. That's not something I've looked at, but if you're going to create special borders for the Super Game Boy for some reason, then that's something you would need to look at. Now then we have our cartridge type. 0 is a normal cartridge, but there are other codes for bigger systems that have bank switching and things, so that's something you would need to look at. We have a ROM size option here, a RAM size option here, the territory of the cartridge, licensee code. Again, this is all kind of not particularly important really for getting started, so you don't need to worry too much about these. The important thing you do need to worry about is the header checksum here. If this is wrong, just like with the Nintendo logo, if it's wrong, the real Game Boys won't run it. The emulators don't care, and that's why I said about that RGB Fix program, which will automatically correct all of these things. Now there is also a global checksum, which is a sum of another checksum of the memory of the cartridge, but I don't believe this is actually used by even the real Game Boy, so it's something not to particularly worry about. And then all the remaining area of the cartridge is the ROM of the cartridge, and if you've got any kind of bank switching, then you can switch between the ROM between the 16K chunks there. So as I said, we don't have any out and in commands, so well, that probably sort of raises the question of how do we get to our hardware, and also well, with regards to the RAM and things, how does that work? So let's have a look at the memory map as the system sees it when it's running. So the first 16K is the first chunk of your cartridge, which we just described, and that never changes. Then the next 16K is the bank switchable area. So if you're using a larger cartridge, when you do your bank switching, that area will change and show different areas of the memory within the cartridge. So if you want to use a very large cartridge, and I believe the Game Boy can support up to 2 megabytes, it's huge cartridges. So you've got that option there. So you've got extra memory in your cartridge. That will appear from A000 to C000, and you can use that if you want. But even if you don't have that, you do have regular memory from C000 to E000, and this is the generic memory within the Game Boy itself. So this is something that we always have. The Game Boy Color, the second half of that is switchable, but as I say, even on a regular Game Boy, all of this memory area is available to you. Now, for reasons that aren't quite clear but aren't particularly useful, that memory is cloned again in the following 8 kilobytes. So I don't know if there's some special purpose for this, so I can't immediately think of one, but just don't think, if you're writing to stuff in the E000 range, thinking, hey, I found some free memory, well, you're actually corrupting the C000 range, so just be aware of that. Sorry, a bit of a jump cut there. I suddenly realised this is an old version of this chart, and there were some lines missing that should have been in here. So there is actually a few extra addresses in here that I missed. So the video RAM is mapped between 8000 and A000. So we do have to discuss those. Now, the pattern definitions that can be used for either tiles or sprites are from 8000 to 8FFF and 9000 to 97FF. There's two sets. The first is 256 tiles that can be used for tiles or sprites, and there's the second bank that can only be used for tiles, but you have to define what address you're pointing to, so you can't use some of the tiles from one address and some of the tiles from another. So it's not massively useful, to be honest, but it does have those two areas. And then you have two tile map definitions, which I guess is used for quick switching between them. So you have tile map 1 from 9800 to 9BFF and 9C00 to 9FFF for tile map 2. Now that's the definitions of the patterns and the tiles and the tile maps, but the sprites are actually defined, the positions of the sprites and the patterns being used for the sprites are defined in a different area from FE00 to FE9F. And we do have the catch that we can't do these during the redraw, so we either need to wait for the screen to have finished refreshing, we can test that, or we copy them to a buffer and we create an interrupt handler and get that interrupt handler to copy them. And then finally, where are our out and in commands? Well, there is a bank of hardware mapped ports from FF00 to FF7F. And if you remember earlier, I said that there were some special commands that would address that area. And that's one of the reasons why we have these special commands, because these can be used kind of like our outC command was, because our hardware ports are actually addressed from this memory range here. And then finally, we have a small bank of memory of 128 bytes at the high RAM area here. And we can use that for our stack or for something else. At the very, very top, FFFF, we've got a special interrupt handler that is mapped there. So that's, again, another special thing that we've got there. And then when it comes to addressing the hardware, as I've said, these are all mapped between FF00 and FF80. And the different addresses have different meanings. And all we need to do is write to them to define, to tell the hardware what to do, or in some cases we can also read from them and see what the hardware is doing. We can't do reading and writing to all of them, though. Some only write, so we do have to note that. So it's pretty simple. We've got some timer functions here, an interrupt flag here, which we can read and write. We've then got some sound functions here for if we want to play music, and it's pretty easy, to be honest, on the sound music. We've got some statuses for the LCD here and here, so we can define things. We've got the option to set the scrolling position of the tile map here. We've got a direct memory address here, which I believe is often used for sprites. It's not something I've used. I haven't used sprites. My Gameboy80 does use the Game Boy Color, but it only uses the tile map, so I'm not too familiar with sprites yet. So on the black and white Game Boy, we do still have two palettes. We have palette 0 and palette 1, and I think this is used for inverting colours. You know, sometimes when you die, your character flashes, and what you can do is you can define the four greys as, let's say, colour 0 is black, colour 1 is low grey, colour 2 is high grey, and colour 3 is white. And then on palette 2 you could have the opposite, so colour 0 would be white, and then okay, so on. And that will allow you to switch quickly between them. And I think this is why if you see the Game Boy Color running an old Game Boy game, you actually do get two different colours of the sprites. And I think this is because it's mapped different colour palettes to the old black and white Game Boy's palettes, but they don't have any function on the Game Boy Color. We have an extra special tile map, which isn't something I've used, but it's called the window. It's an overlap tile map. It's very, very limited, and it's used, if you think of a lot of the Game Boy games, you'll have a pop-up menu that allows you to select your items, or just shows or a non-scrolling area that just shows your lives and things, and that's called the window. It's very basic though, it doesn't have much functionality. We then have a few Game Boy Color options. The CPU speed, we have a port that controls that. We have the video RAM bank, which is how we get to that color information on the Game Boy Color. We have an infrared communications port if you're wanting to write your own Pokemon. We have some palette information here. These are used for defining the palettes. They're quite tricky to use, but again, I've got sample code. You can just copy and use that. So, yep, we need those to define our palettes. And then we've got palette information for the sprites as well. And then finally we've got the Game Boy Color's RAM banks. But even if we're not using the Game Boy Color, or we need to maintain compatibility with the regular Game Boy, we do have some banking options on there as well. And that comes from the built-in hardware called the MBC on the Game Boy's cartridge, and we can emulate that just fine. So there are different versions of the MBC. MBC 1 is pretty good, but there are all the way up to MBC 5, which allows much larger ROM banks. So let's just have a quick look at how to use them. Well, the way it works is quite curious. Of course, the first 32 kilobytes of our system is ROM, read-only memory. But if we try and write to those, the MBC hardware will detect that write and will process it as a command. It actually looks at entire ranges for its commands, but I've just put one sample memory address because, to be honest, it's easier to think of these things as a single address and work with them in that way than putting an entire range and getting inconsistent in what you're using. So I've come up with some here that I've just sort of I'm using as my common ones. So if we write to memory address 0000, we will actually turn on the RAM of the cartridge. This is the cartridge RAM, not the built-in Game Boy RAM. If we write to 2000, we will select the ROM bank number. If we're using a very large cartridge, an MBC5 cartridge, which I think are these 2 megabyte cartridges, we also use 3000, which will define the top bit of the bank number. Then we can write to 4000. If our MBC1 cartridge has built-in RAM, we can select the RAM bank to page in. And then 6000 is a special one where we select whether we're working with ROM or RAM if we've got a lot of ROM and RAM in our cartridges. You can have a small amount of extra RAM or a large amount of extra RAM, or a small amount of extra ROM or a large amount of extra ROM, but you can't have a large amount of extra ROM and a large amount of extra RAM on the MBC1. So again, a bit tricky, but this is another thing that I've got some sample code that's going to be coming. We're going to do a tutorial on how to use this, and you can just work with that sample code. So I just wanted to put some documentation, as much for my own self, because I keep forgetting these addresses and getting confused by them. So a lot of the tutorials I'm doing here, if I need to know something, if I keep forgetting something and I need it properly documented, I'm putting it here for my purposes, and then, you know, I'm sure it'll be helpful to other people, and so I'm making it available. So there we go. So that's a very quick overview of the Game Boy and the Game Boy Color. We are going to look at programming it in an upcoming lesson. We're going to be looking at this tutorial next week. This works for the Game Boy Color, the Game Gear, the Master System, and it also works for the MSX1 and MSX2, because the MSX1 is a tile-mapped system as well. And the MSX2, while it's not a tile-mapped system, it does work quite nicely as one, because it can work faster as a tile-map system than a bitmap system, because it's not really either of those things. It's a blit copying system where it wants to copy large chunks of its memory from one area to another, and pretending it's a tile map is easier for that purpose than pretending it's a bitmap screen. So we'll be looking at those over the coming weeks. Well, there we go. That's the end of this lesson. I hope you've enjoyed it. Please follow my channel if you want to see more about Game Gear and Game Boy programming, and of course all the other systems too. We're going to carry on with more of this in the future. If you want to get stuck straight in, I'd strongly recommend you look at VASM as your assembler for Game Boy, and please go to my website and download the cheat sheet, which is this Game Boy GBZ80 command list here, and that will help you out when you're struggling with your with what commands exist and which ones you've lost. I'll also put my macros on my website in the sources 7-zip file. So if you want to just go ahead and use these to tide you over when you're learning how to work with a more limited command set, or if you're porting your code, these are going to help you. But there we go. And as I said already, if you're interested in this and you want to watch some more videos about Game Boy programming right now from me, then please check out my Gameboy project, which is an ongoing project where I tried to write a game that would work on 11 different systems in just 7 days. And if you're watching that series, you'll know it's going pretty well. So hopefully that'll be something you'll enjoy too. Well, anyway, thanks for watching this video today. I'm sorry about that bug where I had to quickly patch in the VRAM definitions into my website while I was recording the video. I completely missed that. I think I had a computer crash that lost the changes before. But anyway, thanks for watching today, and goodbye.